I flipped the imaginary switch. Try the other one. What's that? Yeah, I thought maybe there was like an over here.
I'm pretty loud.
Yeah.
Well, yeah. Well, the big thing is.
Hey everybody, I think we're gonna get started. I can't make the microphone work, so I'm just gonna holler. So, welcome to AWPUG July. It's July, it's 2016. Welcome. This month we have Josh Marshall, who's going to tell us about async in Python 3.5, he confirms. So please go get some tacos and go get some beer if you haven't had any. Looks like there's enough, so enjoy it. And also, thanks to Capital Factory, of course, for giving us a space. It's really awesome that we can be here and do this stuff. I guess before we start, does anybody have any announcements or anything that, any Python stuff that they want to talk about? No? I'll ask again at the end. Let's see, anything else?
I just discovered that our friends at Amazon have made a serverless Python modules available. Basically, they've tried to implement the Flask-style API on top of their Lambda functions. So I think this is exceedingly cool. And it's in Python 2.7.
That's interesting. Do you know what it's called?
Serverless.
Sorry?
Serverless.
It's just called serverless?
Yeah.
That's
There's
like,
also
is it-
another community called Serverless also that's making something kind of similar, but the AWS one focused on a Flask-like. Flask is in a Flask microservice.
Yeah. That's
So-
very cool.
Yeah, since I'm totally focused on the what I call the no ops movement, just don't want any ops people in my life. Nice people, just don't want them around. Okay, I really like the serverless and the Lambda style to manage databases and stuff like that. And now that since Parsons kicked me off their servers, I'm basically looking at, well, what do I do? Do I embrace Node or do I embrace Python? And while I like Python, I got lots of other reasons that I do it. So the fact that AWS is making it easy to use Lambda functions seems really interesting.
That is really interesting.
For Googling, it's called Chalice. The tool to use it is called Chalice, yes.
Okay. Chalice. You all should check it out. All right, well, with no further ado, here's Josh.
Also, everybody should know that tonight was sponsored by Kevin. So, one, yeah, thanks, Kevin. Two, if you know any sponsors or anything like that, obviously, let us know. So I'm going to be covering, sort of going through a little bit of the history of coroutines and generators and other things in asynchronous programming in Python tonight. So my name's Josh Marshall. I work at UStudio. UStudio is a video management publishing distribution company. And we do a lot of event-driven things. We work primarily with things like Tornado and that. So that's what I'll be talking about. Sort of that experience comes from the day-to-day working at UStudio with those systems. So the agenda or whatever for the talk is, first off, I'm going to talk a little bit about what's the problem we're trying to solve, why do we care about these kind of things, why are these useful inside of Python. I'm going to do a quick run through of what are coroutines, how we've gotten to the point we are now, and then talk through those tools that are coming out. I'm going to be talking a lot about Python 3.5, but I'm going to get there over a little bit. So a few caveats. Again, my experience is primarily in frameworks building on top of a lot of these things. So while I'm going to talk about the lower level mechanics and walk through some of the base standard library things, people who know me know I use Tornado like exclusively. But most of my experience is in systems like Tornado. So if I need to dive into anything, I'll probably hop over into a framework like that. And to be honest, as you use some of this, you're going to be picking your own libraries and frameworks and things to build on top of it. So my definitions of coroutines and other things are going to be very, very much informal. So one, if well, it's mostly defined by what's inside of Python. But two, if you have any clarifications or you see something up on the screen that's a bad practice or whatever, just shout it out, raise your hand. I think that's great. We can collaborate a little bit. A lot of this is sort of new. And if I'm doing something dumb on something that's old, I'd also like to know. So anyway, a quick survey. Who knows, who's comfortable with the concept of a coroutine? Raise your hand. Okay, so then I'll burn through that. Who's used coroutines in Python? Specifically, when I'm talking about coroutines, I'm talking about the new native coroutines in 3.5. Okay, how many of you have used like generator style yield from? Okay, and who's using Python 3? That's just a curious distribution. And who's deploying it to production like regularly? Same things? Okay. And anybody else using, well, I guess there's a decent amount of you, but raise your hand if you're using Node or Go or something asynchronous in your day-to-day. Okay, so a few. Okay, so what are the problems we're trying to solve with this? This is kind of key towards network problems, C10K problem, taking advantage of our compute infrastructure and in IO-bound sort of environments, so a lot of the networking problems that we have, reducing the use of threads or eliminating thread complexity, locks, and other things when they're unnecessary or when they introduce overhead that you don't need. And then I guess one of the biggest points is if you are doing asynchronous programming, you know about callback hell and you want to get out of that. So this is my serial killer handwriting, but you can see a positive side of callback hell is indentation surplus.
Sorry,
But
sorry,
yeah.
can we move the platform a couple of feet just so that
You're
you're
in front of the screen.
Does that help? I don't think I'm able to move this thing. Does that help?
Yeah, that'd be awesome. That's awesome if it's not too uncomfortable for you.
No, that's fine. I'm gonna fall off, but it's fine. So anyway, you know, lots of stuff going on in these if you haven't experienced these sort of callback mechanics. But managing when callbacks are called, where exceptions are lost, information sort of traveling through the different systems, it can get pretty hairy, impossible to debug, all those kind of things. So we want to introduce systems that are better. So what is a coroutine? Here again, it's very informal. We're just talking about a method of cooperative multitasking, meaning you delegate, you actively delegate control out to other coroutines or other processes. So that's a little different than sort of preemptive multitasking where the control can be given up at any point in time. But this also implies some other things. So if you have a long-running chunk of logic, then you are blocking other things from running, just basic principles like that. They allow, again, delegation to other coroutines, reentry, value passing, these other things that make it pretty simple to run things concurrently and start breaking down concepts into more isolated units. And then with asynchronous libraries, coroutines can, again, simplify some of that event code and other things. So if you've used coroutines in other languages, here's a few examples. Coroutines are pretty popular. Haskell has a pretty slick, like, monadic transformer coroutine implementation with arbitrary suspend and resume. After the talk, I've got some links where some people are doing some clever stuff with C, with set, jump, long jump, and doing some assembly things. Anyway, and I guess an important point there is Node is actually, they didn't make it in the last version, but or JavaScript, I guess I should say more so than Node, has async and await keywords that are coming out soon. So I don't know much about them, other than I know there was some influence from Python's approach, I think, in that process. So.
I think those were just like ratified today.
I didn't see that. I know that they skipped it for ES6. There was a lot of discussion, but they.
It was like proposed for a really long time, but today they actually finally put it in there.
All right, so use Python async and wait before JavaScript takes over the world. Yeah. So anyway, I like this quote because it means that we're all writing coroutines anyway. We just may not know it, but whatever. So high level, it's cooperative, it's concurrent, not necessarily parallel. That depends on the coroutine system underneath, and it's explicit, or at least the kind of coroutines I like are explicit. People have different feelings on this. If you've used like G-Event and some of the monkey patching systems before, then some of that's implicit. You don't necessarily know when control is being yielded to other coroutines. My preference is for explicit, and based on the language sort of evolution, you can see that Python is sort of leaning towards the explicit coroutines as well. So how we got here. So I'm just going to kind of build up through everything from iterators all the way through to native coroutines. And the reason why is a lot of these concepts actually pop up later on. So I imagine most everybody's familiar with iterators. Generators you probably use. I don't know how deep people use, how deep people go into sending and throwing and those kind of things, but I'll talk through it, and then building up to coroutines. So iterators are not coroutines, generators are not coroutines, but they share a lot of the same qualities, and so that's how they've sort of come together in Python. We start with blocking calls. Everybody's familiar with this. One entry point, one-ish exit point. No way of delegating control to another process without something like threading or multiprocessing or other tools. So back in January 2001, iteration was sort of baked. This is Python 2.1 or something like that. Iteration was sort of baked in a couple of objects. They proposed the iteration interface with that double under iter and the ability to call next on an object, which is sort of the first example of being able to kind of delegate to additional logic. So again, most everybody, if you haven't implemented an iterator, they're very simple. You just define a double under iter on your object, and then you define a next method. It's double under next in Python 3+, I think I'm getting that right. And then you call dot next on the object versus in Py 3 you call it as it's a built-in that you call on any object. You pass that in. So iterators then, they don't bring language features. The for X and B was already there, but now you can take advantage of it yourself. Obviously, list comprehensions, functional tools like map and filter. And so when we start talking about coroutines, the ability to use those inside of those same processes is important, and how they flow in. Iteration and asynchronous operations are important. So I have if you haven't seen it, that's an iterator. Return self, calls next. Important point here is that you are managing all of the state and the state reentry and all that kind of stuff inside of one function. So if you want to keep track of something, it's up to you. If you want to jump to a later point in logic, it's up to you and your implementation. That's a really important point when we start talking about coroutines, generators, and some of the other pieces. So again, I think most everybody's familiar with this, but that's iterators. That's basically how they work, and they'll come up later. Again, writing complex iterators was sort of involved, especially if you're doing lots of state management, or you're trying to do something like reentry into your logic and manage that. So, go back. Also simultaneously, stackless Python. Does anybody use stackless Python? Anybody familiar with it? Okay, it's kind of old. I say that, I think it's still underneath EVE Online. So it was one of the first, it's like a forkish of Python, and they introduced lightweight threads and coroutines and all those things at the base. And so that encouraged, I guess it was part of the encouragement to go and bring generators into the formal language. And so the key points of generators, and generators flow into coroutines, is that they can return a result, obviously, and then pick up execution right where they left off. So again, I imagine everybody's familiar with generators, but it's all defined with a yield statement, and then you still have the callee-caller relationship. That's one of the disadvantages of how generators worked originally. Like the caller calls into the function, the callee yields out control. There's no real way of you can build some systems around it, but you're kind of tied to that construct when you're getting values back, and there's no way to pass values back inside of the generator at first. But the benefit is Python handles all that state in the stack, not the developer. So anyway, you yield control. I'm going to burn through that pretty quickly. What is interesting though is when when we first introduced the yield syntax, that's when people started building out coroutine-like workflows without some of the helpers that would come out along later. And the reason this is important is as you're digging into asynchronous libraries and people are migrating over to new standards, you're going to see some funny things. A lot of that's vestigial. And you're going to need to sort of understand where they came from so that you know how to port the library or how to wrap around the library. So if I say, let's see, where are we? Yeah, this is kind of a fun example. I need to close my sessions. Okay. And nope, not yet. There it is. So in this instance, like if we were gonna build out coroutines with just yield, you have you need to build some sort of state sharing object. In this case, I have a really simple future object that you can iterate over, and it's going to return await sort of flag or a done flag when it's set. And the internal, because you can't get a value inside of these base generators originally, you need to keep that state, you're like sort of sharing that state between the future and the generator itself. So you need to build a trampoline or dispatcher or whatever, sort of organizing the caller and callee relationship, and then we're iterating over this, and when something is updated, then we're calling back saying, hey, you're re-entering. And this is just a very, very dumb, lightweight version of what people were building pretty complicated structures around, including some of the monkey patching and other things. So you can see the sort of the disadvantages of what yield, if you're trying to build coroutines on top of just generator, just yield, some of the problems that you need to solve. So that's yield-based generators. Meanwhile, again, more influence. You have Twisted coming out. You have Greenlit and other systems popping out. So moving forward, we have a PEP that allows us to start sending values inside of the generator. And that, now we have real message passing, right? And so this is where, if you're talking about things like Tornado and some other systems, when you have gen.coroutine and other things, you have the ability of now passing values in, and probably just as importantly, you have the ability of throwing an exception inside of that state. So I don't know how many people are using generators with send, implementing these things, throwing them, like throwing exceptions to maintain that stack trace. But I'll show you a real simple example, which is, let's see, yeah, yield gen send. So this is the syntax if you're not using that today. And then here I'm iterating over the generator, sending in new values, and I get a stop iteration when it's done, and then I close it to perform any follow-on actions, and then I can actually throw exceptions. This is kind of, I think, one of my favorite parts of it. So if I run, too many zeros. That you can see in the traceback, it's actually the outer function calls throw, and then it shows me where that's raised. So that started helping break down debugging and digging into systems. Yeah.
You very quickly went over the concept of message passing.
Yep.
And I think this is very tightly engaged into the concept of coroutines and not really acknowledging and communicating sequential processes and how it's so robust as an asynchronous pattern is. I want to encourage you to, if you could opine a bit more about that, because
Sure.
To me it's critical to any asynchronous process.
Well, one of the key things here, I think, I mean, there's a lot of different benefits to it, but to me, I look at it and you start being able to really separate out your implementations. So previously, we had future objects, we had this shared state, we had other things having to modify values, and there's no real way to flag it. But here, I can have pure values being passed back and forth between my coroutines. I can be passing in information. It can perform its own logic at that point in time. I can be raising exceptions and letting it know what's sort of happening outside the scope. That previously, what you could only provide to the caller, now the caller has additional scope that can provide in. So I think I'm trying to move pretty quickly because there's a lot of stuff, but the message passing is really important, and that comes in when we have the new keywords and we have yield from, because yield from is actually, well, I'll dive right into it, but that's an improvement on the message passing. So anyway, that's generators with .send, and if you had any points, feel free to add them if there's anything.
I guess my big point is that the coroutine model makes it easy for you to get to a stable asynchronous pattern quickly,
Mm-hmm.
right? And it's so hard to do asynchronous coding. Here, the coroutine model is actually helping you become right from the beginning.
Right, and you're throwing away things like callback structures and all of those things, right? You can see that it actually looks and feels mostly like blocking code, which is easy to reason about. And you can start chaining them together, which makes it nice and portable. So if you change your outer contract, or this is delegating to another object, you can easily port it around. So anyway, we're still moving forward, though. It's still not perfect. Again, we're constrained to that caller-callee structure, so you have to build out as a framework these sort of complicated yield structures. If you have an event loop and you have individual generators calling their own generators and yielding out, it gets a little involved. So simultaneously, again, you still have the growth of these individual frameworks that are pushing more and more requirements on these coroutines on the Python language. And simultaneously, we have Python 3, which everybody's using, and that was immediate adoption. So it's all great. No, but there was a little bit period in there where Python 3 sort of came out, was stabilized, was finalized. They weren't adding a lot of new constructs to the language, and then once they sort of got to that about 3.2-ish, I think, that's when they added some new things. To me, what stands out is the ability to delegate to a subgenerator and pass that subgenerator all the way out to calling generators. And this is the yield from syntax. So raise your hand if you use yield from. Okay, so it's a decent chunk. Again, it's got all the benefits before of the sending and the exception throwing and all those things, but the real benefit is, here's my terrible drawing, I can call in a, my outer function can call into a sub function that can delegate to another generator, and that generator can be delegated all the way out to the outer generator. And so now I've got message passing and exception throwing and sort of state reentry. Those middle pieces can just become lightweight middleware, and they hop out of the process. Sure, it reduces some code if you just want to yield from a range or something like that, and then you save 1 or 2 lines of code. That's not the real benefit. The real benefit is that now you can sort of tie these message buses all the way through your stack. So yield from is pretty core to how asynchronous frameworks have been developing in Python. Let's see if I actually want to. I mean, that's pretty much it. I have this example here where I bounce the outer function, calls into gen 1 then calls into gen 2. This yield operation here is actually coming all the way back out as a result of send. Sending is actually sending all the way into that inner object, and this middle gen 1 function, this middle yield is just an outer byproduct for a little bit. So if I say L6 from, you can see that middle yield from, inner yield, now I'm all the way back out to my outer code here. Outer receives a 0 from the inner yield, then it passes in a 3, and the inner yield immediately picks up. The middle yield doesn't intercept it, doesn't need to intercept anything, and then the middle yield gets the result from that. So anyway, returning from those yield from values and passing those generators out is yield from. So that's that. A lot of, you have standardization across, well, actually not standardization, but you have Tornado sort of becoming one of the asynchronous libraries that's widely used, and it's got its own approach. You have G-event, multi-patching, and some other things becoming a standard approach. You have async core and a couple of options there that didn't really see high adoption. And then you have Twisted. It's been around forever, but sort of it has its method. Competing non-interoperable libraries. If you're wanting to do asynchronous programming in Python at this point in time, you sort of have to buy into one of your communities and then build your own asynchronous libraries if they don't exist, or cross your fingers that somebody else likes the particular event-driven framework that you like. So there's a lot of repeat work being done with not a lot of benefit to it. And then also, like, about this time, everybody's cool with callbacks again because Node.js became popular. So
That's not true.
anyway, that sort of popped up around that time, and so I think there was a renewed, if anything, there was a renewed interest in asynchronous programming in Python because Node made it more popular and more folks were doing it. At least that's the way I felt. Nobody really cared about Tornado or some of those other things. The broader community didn't, right, for a while. So now we've got these competing non-interoperable libraries, and that lack of portability is, again, creating that duplicated effort. So Python, with a couple of PEPs, they introduce asyncio, the new project. So that actually came from Tulip. Tulip was, it's Guido and a couple other folks, I think, who built that originally. And then they introduced it in 3.4 as a provisional, but they were pretty confident it was going to make its way in, and then 3.5 is when it became final. So asyncio was driven from that yield from concept. So now that we have the ability to easily pass and delegate subgenerators, we can have a system that everybody kind of comes along and standardizes on. And so it's pretty familiar if you've used some of these asynchronous libraries. So if you, as a Tornado dev, it was immediately obvious. Tornado tends to use more yield and wrappers. Asyncio uses yield from, but other than a few things like that, it was easy for me as a Tornado dev to hop over and start taking advantage of async. And one of the positives is Tornado and some of the other libraries were designed with a replaceable loop, event loop from the beginning. So adopting asyncio is pretty simple for them. So basically, when you break down asyncio, you have an event loop that is platform specific, at least the one in the standard library. There's a event loop what's the word I'm looking for? Interface that's sort of standard. That other folks have already implemented. There's a UV loop and some other pieces. But you have the base event loop where async IO determines what's best for you, KQ versus other things. They emphasize transport and protocol separation. That way you can have individual libraries taking advantage of it. So Tornado's HTTP or Twisted's IRC. I don't know how far along they've come in porting, but that's the idea behind it, is you separate out the transport and protocol and you can separate out those individual implementations, and they're not tied to the library itself. So async IO does not come with an IRC library, an SSH library. It comes with just the base TCP, UDP, a couple of base capabilities there. Also, another important point is they didn't require this yield from coroutine to be part of the system. That's what they use internally, is you're not going to be using it before 3.4. But I'll show you some examples where you can be using raw callbacks if that's the way, if your library is expecting raw callbacks, if you're needing a future object, so there's a future in the standard library. Some of these other libraries have their own future objects, like Tornado and other ones, so you can reuse those if they fit about the same model. And then coroutine is sort of the helpers and the wrappers on top of it that make it even easier to get started. So they do have a lot of flexibility. It was designed for interop from the beginning. That's an important point when you start talking about what's the future of some of these libraries. So anyway, you have a lot of different coroutines. They can now easily delegate to each other, depend on each other. You can chain them and other things. So now I can show, we're still not to the await and async here, but I can pop open. Let's see. Let's start with async IO. So this is the way. If you haven't done it before, it's pretty basic. You wrap the functions that you want to be. Can everybody see that code okay? Can you be larger?
Larger is better for my own.
All right. Is that good? Okay. So you wrap a function with a decorator. This indicates to async IO that it needs to be returning a future, building up tasks, other things. And then you yield from, this is that new language construct where we're passing that out however far it needs to go into the event loop. And other pieces, your individual functions then are implementing async IO coroutine, and that's pretty much it. So it makes it nice and easy to read. Again, we get all of that nice exception inside of the context of the application. Called exceptions being raised inside of the context of the application code that I'm working on. So in this case, I have AIO HTTP, which is an external library. It's not part of the standard library, but it implements a simple little somewhere between Flask and Tornado's HTTP server interface for the server, and for the client it's kind of request-like. So anyway, you can see that I'm yielding the response to get the initial object, and then I'm yielding on the body. So you start breaking down these individual tasks. Anytime it's an IO-bound task, you're going to be yielding out, but it's substantially better than the callback-oriented workflow or even the yield workflow that we were showing before. And so in this example, I'm actually spinning up a server and a client on the same event loop. That's useful if you're doing things like testing and other pieces. And running it, I've got the same encode. It's doing a binary TCP, just real simple. Take JSON, put a length header in front of it, and then send the JSON message. Very, very simple. And the real value, or the valuable code, I guess, is down here. I'm iterating over a couple of different URLs. I'm building up an async.wait, which is allowing me to say take 2 asynchronous tasks, and I'm going to wait on the completion of both of those. So you can see here, run until complete. So async io.wait takes 2 tasks or 2 awaitables, turning them into one that you can then depend on, and that's how you can start building up some of those chains. And I'm using the built-in get event loop. I'm not constructing my own or anything like that. You can also do that. But I'm using the baked-in event loop, and this is going to block until tasks complete. And that's pretty much it. So then I've got a couple other examples here. I don't think I have any exceptions. Yep, so anyway. Pretty basic example, but that shows you yield from, that shows you async IO, and that shows you AIO HTTP. So that's a couple quick. Oh, you quit that? No. Okay.
Just to clarify, basically you made a web server there with async IO.
I'm calling a web server. There's actually 2 components here. Nope. So there's 2 pieces. One is here I'm calling two different URLs. So I'm saying Google, ustudio.com, go fetch those simultaneously, let me know when they're done, and then it prints inside the body of those requests. It lets me know, that's down here, fetch. It lets me know when they're done, the status I got back, and the content length. So that's one. And then the other example here is I have a basic TCP server. So I'm asyncio opening a new connection, and then I'm just putting a single client handler on there. So every new client that connects, this handle gets run. And then I'm also making a client here. So server and client. The server, all it does is, let's see, handle message, read message. So it gets a reader, well, that's actually handle client. So for every new client, I get passed in, I get a reader and a writer for that object. In this case, I'm reading from it using yield from. The first thing I'm doing is getting the, a 4-byte integer, and I'm saying that's my length, and then I'm unpacking it. This is actually a side benefit for Python 3 plus for those of you who are still using a lot of Python 2.7. The binary and string, the bytes versus string, moving between those, the more enforcement, it makes it a lot easier. If you've dealt with a lot of, is it a string, is it UTF data, is it Unicode, is it a byte array, all of those things, at least for me, they pretty much have gone away since I moved over to Python 3. So that's a recommendation. But anyway, I'm decoding JSON here and passing that out, writing in the same thing. It's pretty simple, and I can toss this code up on GitHub afterwards. But the benefit here is that I'm putting both the client and the server on the same event loop. They're calling each other, bouncing back and forth until it finishes. So that's asyncio. Any questions on that? Okay. Digging in a little further, again, one of the benefits with asyncio is that you can start doing hybrid. So you can use Tornado, or you can use any of the other libraries that have sort of come along and support asyncio. You can use different event loops. So in the next example, I have, hybrid, nope, not that one. I've got a hybrid example where I actually use Tornado code and asyncio code together. So you can see asyncio code, same thing. You've got the asyncio.coroutine, you've got a yield from. Here, all I'm doing is sleeping. These are very, very simple examples. But then the Tornado code, I'm using Tornado's coroutine system. So gen.coroutine, that's entirely Tornado. You can see I'm yielding, not yield from. Gen.sleep is Tornado's. It's wrapped around their implementation and callbacks, timed callbacks and other things. They're pretty similar conceptually how they work, but they're actually two completely different implementations that started on two completely different event loops. But in this case, I'm making Tornado work with asyncio. Tornado actually provides the ability for me to invert that as well. Asyncio, just as a side note, has in general better performance than Tornado's raw event loop. So if you're using Tornado, you can use asyncio. UV loop, I think, is supposed to be even better. I haven't done the performance tests myself, but anyway. So you can see here, I'm getting a task from my asyncio timeout, and then I'm actually wrapping the Tornado timeout with a method here that's provided by Tornado into an asyncio friendly future. I'm taking both of those, and now I can mix them together, chain them, and wait on both of those to complete. Again, two different libraries, now sharing the same event loop. Everything else is sort of their own custom implementation. So in general, that's the promise of it. Tornado can go, somebody can go and implement a database driver in Tornado. Somebody else can go and implement an HTTP client or whatever inside asyncio, and you can use both of those implementations in the same library in whatever you're building, and you don't have to, you don't have to hope that somebody writes the same database driver in the framework you've chosen. You can go write your own sub-libraries.
Do the event loops run on different threads?
I mean, they can, but not in any of these examples. It's all in the same thread. Yep.
So there's like a master and a slave, or?
Well, technically you get far enough away and there's sort of like the event loop is delegating to a lot of different things, but the goal is that you eliminate master and slave as much as possible. I mean, if something else needs to depend on the execution of another one, for instance, a URL fetch, and I need the response, well, there's a natural sort of caller-callee relationship. You're not necessarily going to break that down, but underlying the system, those small sub-blocks of execution, there's not really a dependent system. They're just each iterating over and then the outer event loop determines who gets called next and what gets scheduled and what gets canceled and all those other pieces. So again, coroutines, you want to start thinking about them as parallel objects more so than a strict dependence on each other. Does that make sense?
I think so.
Okay. All right, so that's the hybrid. So now we get into one of the downsides of that. You saw that there are decorators. If you don't put a decorator on it, you will get confused because, things aren't waiting on things or running at the right times, or things are getting lost in the process. So you got to make sure you have your decorators on the right functions. You got to make sure that you're yielding the right objects and other things. There's no real protection inside the language. It's all these wrappers around yield from and generators and other pieces. So if you don't catch values in other pieces, you will lose futures, you'll lose values, you'll actually lose runtime. You thought that it actually saved a database record, but because the prior callback didn't get called, it actually never saved it. It just gave you the sense that something successful happened, which is not fun. So at this point, that's when they introduced async and await the keywords in Python 3.5 to make it much easier to wrap some of some of the generator concepts into a more structured, more language protected model. And that was, again, I think that became real in September of last year, whenever they launched 3.5. So what this introduces is a native coroutine type, which is different than generators and different than iterators, but it's designed to work in collaboration with those. And there's a few new keywords, and I think it's personal preference, but I think it's substantially more intuitive, especially when you're debugging and running it, and some of the things that they do inside of the system to let you know, oh, you didn't handle this future, or this thing got lost. It'll actually tell you when those things happen. So I think it's a much bigger improvement. So you have proper coroutines, indicated in this case by async in front of your function declaration. You're waiting on values indicated by await. You actually have with context now, so you can asynchronously build context, and then you can asynchronously iterate over objects. This is why when I talked about iterators before, you're going to need to know some of those same pieces when you go and implement a asynchronous with context or a asynchronous iterator. And I'll show you like real code there. Example. So if we look at this, what I'm building here is a fake database object. So I've got a new class. You see here immediately, actually I'm going to invert it a little bit. I'm going to start with a simple thing. We get another event loop. We call this wait function. The wait function returns an awaitable object that then gets wrapped by the loop into a task. I'll talk about that a little bit more. But that's all just happening for you. So I take an awaitable, I pass it to the event loop, and then it's going to operate again on that asynchronous with context, return a session, and then I'm going to asynchronously iterate over the values, and then asynchronously update a record. And all of those things, it's happening in a very simple, easy to understand. I mean, the only thing that's changing is there's an async operator in front of these things, and now it's protected by the language and other things. So then if I scroll up, go back into the session is defining a with context that's actually returning itself. It's also implementing an iterator. And the only real difference there is I'm putting async in front of it and then defining a enter. I can do whatever I want to here. I'm just sleeping, but I could be opening up a connection to the database or validating credentials or doing any number of different things I want to asynchronously. Then I return myself. I can be cleaning up in the asynchronous exit method. And then you probably, I mean, in a real world, you'd be returning something like a cursor or something else, a different object. In this case, I'm just keeping it simple and making the session itself an asynchronous iterable. So I'm returning, I'm setting up here a couple of fake records, right? In this case, I might prep the cursor or send the query over to the database or whatever if it was an actual database library. And then I'm implementing a next. So this should be all very familiar to the iterator construct, and if you've done your own enter exit with context, it's all pretty much exactly the same. You will notice here that instead of stop iteration, which is what you would have implemented in a generator or iterator before if you're manually doing it, it's stop async iteration. That's so it can you can still have both. You can have both of those play together, for loops and asynchronous for loops in the same sort of context. And so here I'm just, again, the only asynchronous operation for doing any of this is waiting, but just to show you that you could be doing whatever you want to there, chaining those things however you want to. And then I'm actually not doing much in parallel here. It's actually all sort of chained operations. There's this little updating record. I could just as easily say, well, actually I'm iterating here. I could build up a list and then update them both simultaneously in one of those async.wait, build a task dependency if I wanted to. You've got a lot of flexibility how you want to build it, but hopefully what you're seeing is compared to callbacks, compared to even the yield from generators and other things, this is a substantially better model, and you're using existing Python concepts to go and build out those objects. So that's async and await. A quick introduction. Let's see, what's next? Oh yeah, so we can have a little fun with that. Now we can actually use, actually I'm going to show you a hybrid option real fast. So again, same deal. We can use async and await with both Tornado. This is the exact example I gave you before. You notice I've thrown away my decorators, I've thrown away my yields and yields from, and I'm just using async and await directly, and I can use the async IO sleep and the tornado sleep together. Same deal. I'm patching tornado's loop to use the async IO loop, doing the same thing with the future objects so they can play together nicely, and it's running. And this is a little bit briefer, a little bit easier to understand, and a lot less error prone because I can't await on a non-awaitable, a function that doesn't return an awaitable. I can't call asynchronous operations on something that's not identified as asynchronous. It's just a much, much bigger improvement for those things. I have an example here where I'm doing asynchronous operations on standard in. So this is a terminal example. So I'm just looking standard in. I'm adding a reader. Anytime there's a read event ready, it's going to hit a callback. Now, first off, I want to call out that even though I'm inside of an asynchronous function here, this is a standard callback-oriented process. So like I was saying before, at the base level of loops and some of the other pieces, they still allow you to build base callback workflows. And that helps integrate existing libraries and other systems that don't understand async await, don't understand yield from, maybe don't even understand generators as a coroutine concept. They're doing it all in callbacks. So in this case, I'm calling add read, and then once I've added the listener, I am going to move into a proper asynchronous loop here, where I'm just going to wait until and run tasks as they're added to the system. Now, I could be using a system for message passing than this shared state list here. For the purposes of the demo, it works, but that's just a encouragement for you to probably break those things up a little bit. On read, when I get this read event, I know there's a new line or there's something to be read here. So this is important. This is a blocking call in the middle of my asynchronous operations. So you need to make sure that when a read event is ready, it's actually the right read event and other things. You got to be writing some protection so that you don't block on this forever. You need to always wrap things with timeouts. Make sure that even if you think you know what's going on there, that you're covered. I'm not doing any of that here. This could block forever if I wrote something incorrectly, but that's an important point when you're writing asynchronous. You still need to be thinking about, am I calling a blocking function in the middle of this? If so, how am I limiting that, keeping myself from blowing up the whole server or the whole backend system? That's pretty much it. So this thing, there's not a lot that's parallel with this, but I think, yeah. So if you're a Douglas Adams fan, that's all it does. So, but that's asynchronously pulling from standard in. So, as I said before, the point of these is that I can start stacking them together. So I have a terminal coroutine system, and then I want to, let's see, I always forget my names. So here I've got a system that asynchronously generates an audio stream at a frequency that I pick. So again, it's got this asynchronous start. This is going to return the task, the future object. It's going to iterate over and just continuously send out 8-bit unsigned integer values indicating amplitude and other things. And so I'm going to bypass all of the actual writing. The main point here is, one, I'm doing blocking writing here. I could replace this with a synchronous write, and that's that's valuable. Again, one of the trade-offs here though is when you put something into an asynchronous workflow, it gets put onto a event loop, which means that you're not guaranteed when it's going to run. If you're doing something like audio and you want it to be playing somewhat seamlessly and you're streaming that audio out, you're going to want to be reducing your buffers, reducing your callback time, other things. I'd like to say that's why I put it in here. I put it in here because it's simpler than actually wrapping that with a writer. But they are things that you have to think about. In fact, early on in Tornado, Ben Darnell, one of the main author of and maintainer of Tornado, he actually said, like, when you're making calls to database, sure, it's great if you have an asynchronous database driver, but you need to be thinking about it because if it's faster, for instance, Redis is actually faster, the call, it spends less time in compute overall, making a direct key call than if you turn it into a series of asynchronous requests just because of how much it's moving between different contexts. Something you need to measure, something you need to understand on your own application. In this case, I'm just writing out those samples within a decent time. I am sleeping here in between each write cycle for 0.05 seconds, and then building up the samples for whatever I missed. And in this case, I think
That's standard sleep, so that there's no real time-based accuracy.
well, this is asynchronous sleep, right? So it's sleeping at least. That's the guarantee. But that's what actually we'll show you some unit tests in a little bit where you have to always.
If you're gonna make sound, time-based matters.
Yeah, exactly. Yeah. So this is a very imperfect. You're actually going to hear there might blip out a little bit as it's waiting on the callbacks. So in reality, you might turn this into a threaded structure or something like that, where you have a more direct line out that is blocking, that is a little more reliable, and you're tossing on at a rate is faster than what's necessarily getting picked on the other side, and rate controlling somewhere else, so that you're not dependent on the callback cycle for any gaps in it. For the purposes of this example, though, hopefully it gets the job done enough to indicate it without being too complicated. But this, so there you hear that blip. That was probably in a callback. Those little points. So it's just making a quick sound there. So now I have a terminal writer or a standard in listener that takes commands, and then I have a library that takes arbitrary frequencies and writes those out. So then what I can do is combine them together, and now I have, I'm bringing both of those in from the outer object. I'm going to start them both. I'm going to wait on them both, and I'm actually going to, in this case, my terminal takes a callback every time there's a new line to iterate over. I've got a few commands on here, which I'll put this online. You probably don't care about all the details, but I've got a few things. I can call a chord. I can make a beep. I can actually evaluate a whole string of commands. Stop it. And let's see if this is all going standard out too, so if I forget to pipe it, it just fills my screen. All right, so if I say chord, let's go for 1 second, 60, 63, 67. So, okay, we have a chord. So then, that's important to catch your actually this is good, I can show you. This is the kind of stuff you get with this Async 08, which is great. So I control C, and I just killed the event loop. And it tells me in here there was a task that was cleaned up, it's garbage collected, but it was still pending. It wasn't captured, which means if that task had an exception or had a return value that I cared about or something else dependent on it, that's important. This is something you didn't have before. It's just like, oh, cool, you killed the loop. I don't care what I have in my list memory of different things to call on. This is substantially better. It's something baked into language now. So in this case, I can now, because it's just taking standard in, I can send a series of commands to that same thing. So if I say cat commands, Python, which one was it? 14, music, play. So anyway. So it's that easy to sort of combine some of these coroutines, put them on the same stack, pass values between each other, and I mean, I could take some of these other pieces, the asynchronous HTTP client, tack it on the same system. It's really easy to start chaining those together. So that is combining those pieces. I think that covers it. So I'm going to move now. What time is it? Okay. So I'm going to try to burn through pretty quickly the next stuff. It dives a little bit deeper into async IO. Yeah.
So is there a, you
I don't know that there is, but there'd be absolutely no reason why gevent couldn't go and swap this tomorrow. You don't know what's underneath. You don't have to worry about passing in loops or yielding anything or putting any new keywords. So it doesn't matter what they put under the covers. I mean, they could swap it all for a threaded implementation tomorrow. You would, right? Like you wouldn't necessarily know. So there's no reason they can't. And I actually would imagine that they are if they're not already compatible. I know gevent authors, Tornado authors, Twisted authors, forgetting. There's another library in there. All of them were involved as asyncio was sort of being planned, and they were early on like giving feedback on, hey, Tornado can't move the event loop because of this expectation, or I actually don't know any feedback. I see it from the Tornado lens because of the mailing lists I'm on and other things like that, but those processes fed into the design of it. So I imagine gevent will be porting over soon if they don't already have pieces. But again, the nice thing about the monkey patching is you don't have to worry about it. The downside is you have no way of debugging it or knowing whether it was calling blocking or it was set up properly. So that's a personal preference. I prefer the explicit. But so immediately after asyncio came out and some of these other things, people were like, oh, this is the death of Twisted, this is the death of Tornado, it's all gonna be in the standard library, all I have to worry about is asynchronous IO. And that misses the whole point. The whole point is that you've got these communities of people. I mean, you look at what has been developed in Twisted over the last 15, 16 years, all of the different protocols, all of the different sort of battle-hardened systems that are built with them. And if it was nicely portable with whatever small micro asynchronous web framework you want to use tomorrow, or with a couple of database drivers for new things that, for whatever reason, Twisted doesn't support, that's a positive. You're actually bringing these communities together, and this is a strength. They were all explicitly brought into the process. So a part of that is, here's all the stuff that asyncio doesn't provide that you're going to have to go figure out. There's not a built-in HTTP client. There's not a built-in HTTP server. There are basic things like TCP and UDP server and clients, but that's it. You've got to build up your own system on top of it. It doesn't have any existing database drivers, as far as I'm aware. I might have to take that back and go look at a couple of the built-in like SQLite and some of those pieces. But for most use cases, you're not going to have anything in there I think that you really want. Again, all the wire protocols for TCP and the services that you're using, you're gonna have to go build all those out or find someone else who's doing it. Testing helpers, I would love to know if other people are finding that, but I haven't seen in standard library any real testing helpers. And so I'm gonna walk through testing some things next, but if you guys know of any like out-of-the-box testing frameworks or really robust testing systems for these, let me know. It's pretty straightforward, but I'm always looking for those things. But those are all things that don't come with asyncio that you're going to have to go backfill. So anyway, I can list a bunch of other benefits of coming over to 3 anyway, if you're not already there, specifically for network services. Again, that string, Unicode, byte data workflow is so much better, especially when you're writing to TCP sockets and reading from sockets, and it enforces you to be thinking about what character set your data is coming back in and whether or not you've serialized it properly and all those things. So anyway, let's see, just about done. I'm going to show you what testing it looks like. I'm going to show you 2 examples. One is what a test looks like with just base asyncio. So the first thing is I'm running nose. Nose does not know about asynchronous test cases, at least unless I'm missing a flag. Again, if anybody knows about anything, let me know. But nose will just pass over those and sort of break on them because it'll return the value from the function, thinks it's great, but it needs to be awaited. So what I've got here is I wrote a quick little decorator, and I mean, it is super simple. All it does is wraps the method, it sets up a timeout in case the test runs too long. That's even optional if you don't mind if your tests just hang forever. You don't have to have this. And mostly, it turns it into a blocking call, right? It sets up a loop, says, give me back the awaitable from that method, and then wait on that. That's all this really does. And now I can run actual async test methods. This one's sleeping. And this is what we were talking about before. The sleep is not a guaranteed anything at this point. It's like, it could, it's going to be somewhere around there. I think it's guaranteed to exceed that time, but your tests can get into trouble here. I guess they always can. If you depend on sleep being super accurate, you got other problems along the way. But anyway, so there's 2 things here. I should be getting assertion errors, and this one should work. So to be a proper testing over. So run it. Nope. Nope. Oh, that's L. So it's got, I mean, these are sleep functions, so they take a little bit, but then this one should time out after 5 seconds. So you can see, again, we get a decent trace back and understand what happened there. So that's testing in async IO. And then just to show you, like, again, it's pretty simple and straightforward, but if, this is one of the benefits of something like a Tornado, where Tornado has testing built in, and it's got a lot of helpers, so wrapping their web applications and clients and other things. So I played a little bit with it, but I didn't get this working with the async IO event loop, the Tornado test case. Their tests, while their primary implementation is pretty flexible, their tests sort of expect a little bit more built-in Tornado functionality. But this is the kind of stuff that you get from an existing asynchronous library. Is very quickly, I have the built-in Decorator, and now I can build out these asynchronous tests easily, and again, lots and lots of other helpers around network services and other things. So anyway, that's Tornado testing. And then let's see, I think the only other thing I was going to talk through here is basic functions of async IO. So, and now I'm implementing everything in a test environment. So I've got a simple awaitable function here, and in my setup, I set that timeout issue. Everything here, these are all blocking tests because of the nature I'm working here. So a task, well, actually, start with a loop down further. You have a simple event loop which exposes a few methods like create task, create future, run until complete if you pass in an awaitable, or run forever if it's a server, and then you can stop it other times. So every loop needs to implement some of those pieces. Now what's slick is the fact that it's returning its own future objects and task objects, because all of these individual libraries had already implemented things like that. Right? Tornado has a future object. There's a built-in future object that async core and other things used. So the event loop itself is responsible for delegating future-like objects and task-like objects and awaitable objects. So in this case, I was able to install UV loop, set that up as the core loop, and then run whatever I want to here. And I've got an assertion here that's asserting that I'm actually running on a UV loop. But that's the loop structure. The next thing that you build on top of is probably futures. Tasks and futures are kind of similar. So you create a future here. For those of you who don't know, a future is just an object that sort of holds that result status and triggers when it's done processing, whether because an exception was raised or the return value is set. So in this case, again, this is all like standard callback style. This isn't using any async await because the lower level mechanisms are friendly to that. So in this case, I'm saying, hey, the loop, one of the other methods on here is call at a later time. This is at least 1 second in the future. Call this callback. This callback is setting the future. And then when that future is done, so futures have to implement an add done callback. When that's done, call the stop function, which stops the loop. So I'm going to be blocking here forever until that process happens, which is going to be in about a second. Both those things are going to trigger. And then we'll get a return. The future itself, when I call result, it will return that value. If there was an exception raised in that process, that exception will be raised right here. So a key note here is as you're doing these things, if you are passing lower level futures around versus working directly with async and await operators, make sure you're closing out your generators and calling results, because you might lose exceptions if you're not doing that. Again, I think the goal would be to be using async and await at the high level. The last part is task. Task is actually a subclass of future, and it's a wrapper for async IO that has a little bit more around the stack and some other execution pieces. And it can take a coroutine as an argument. So it's building out the futures internally. It still has an add done callback as a future implementation. And I'm stopping the loop here. And if I were to say, run until complete and pass the task, and I would get the result value back from run until complete, and other things. So that's a high level, a couple of pieces of async IO. The main parts that you're going to be working out at the lower level, and everything else sort of builds on top of that. So there's, again, TCP, UDP helpers in there, stream writing helpers. You saw me earlier passing in low level file descriptors. In that case, it was the standard N file descriptor, and then performing callbacks on that. All of that is also in the asyncio library, but that should get you started if you're building, especially if you're building lower level asynchronous functions. So a few gotchas as you're doing these things. One, take all this with a grain of salt, it's all my opinion, but supporting explicit loops to your processes, especially if you're calling something like asyncio.get event loop, that's depending on the implementation, but it's depending really on a singleton in a lot of cases, or the current state singleton. And that can get hairy when you're testing, when you're trying to divide things into different processes. Maybe you have a threading sub-processor wrapped around a coroutine event loop over here, and you've got your other one over here. You want to keep those loops separate. If your code doesn't provide a mechanism for passing in a loop and customizing that, then that can create some involved problems. I think it's actually in the PEP that all functions in asyncio that make operations on a loop should optionally take it in as a value, the loop instance. And Tornado is the same way, and that's why I'm saying it like I burned myself by not implementing that later, and then my tests don't work very well, or it blocks on a wait because it's not sharing the same IO loop, and it's just a mess. So anyway, support explicit loops with your libraries. Make sure you handle result. We talked about that. In my opinion, prioritize async plus await. Fall back to yield from only if that's for some reason the event library doesn't handle wrapping those yield from things into an awaitable object. And then very last is callbacks. Those things, it's just too easy to lose context and not have something set up. I mean, obviously write your tests so that you can catch that as best you can, but async and await is you should probably try to standardize on that. Make sure you wrap hybrid futures. So if you're using a Tornado future or something else, turn it into an asyncio compatible future. Trying to mix testing frameworks. Like I said, I tried to do a couple of those things for this, and I've tried to do it in other projects. Really try to standardize on one testing framework. You can decide how much you trust running one event loop for your testing framework versus another loop for your actual production deployment. That's totally your call, and I understand not wanting to do that. But if one testing infrastructure gets you moving faster and it's easier and you can wrap the existing concepts in that, it's probably going to be easier than trying to mix a bunch of different testing frameworks and their feelings on the IO loop. Python 3.5 isn't everywhere. Python 3.5.2 isn't everywhere. So Python 3.5.2 adds the create future. So if you have something that needs a loop-dependent future object, like UV loop was one of them, I believe, that needed that, then you have to have 3.5.2, which you're not going to find in a lot of base installations and other things. So anyway, and then the gotcha around Python 3.5 plus custom deployments plus Python packaging in general is just, I don't really have any good answers. It's just fun. Say again? Docker solves everything. Yeah, install Python 3.5 on there, and you don't need to package Python at that point, right? And Chalice and Serverless.
Serverless,
Yeah.
future is now.
So that's pretty much it. I had a couple other files that I just skimmed past because I was droning on too long. But there's a few links. Really, it's a little bit old. It's a little bit old now, but this is from 2009. David Beasley goes through, if you haven't seen it before, he goes through an exhaustive, he actually builds up a mini operating system with coroutines throughout the course of it. And that's 2009. So I don't think he had yield from at that point. I think it's all yield. He did have send and throw and some other pieces, but that's a good guide if you're sort of trying to get your head around it. And the coroutine article on Wikipedia actually is pretty solid. So I recommend that. And then here's a couple links for some real fun implementations in C that do some scary stuff. One of them actually says, it talks about your employers dragging you from the building, like the security, if you implement this at work. So if you want to look for some fun. And then this is sort of a G event, gives some insight into how G event goes about it, how G event I imagine is going to sort of look at bringing some of these pieces moving forward. But that's it. There were actually a lot of other links here, but that's all I got. Any questions? Anything else you want me to dive into? Any of those files you want to see in more detail?
Twisted has got the concept of a rate, a task like 10 hertz, 100 hertz, but it's regulated, not like just delaying 10 milliseconds in between events. Is there a similar concept in the new language features?
I don't think that my immediate response, I don't know. I don't think that you're going to find something as robust as Twisted in that, probably. I mean, that goes for a lot of, like, pretty much anything Twisted's implemented, I'm going to feel like that's going to be more robust, more feature capable, and probably more accurate than the other ones. I don't know of anything exactly like that. I mean, you've got your sleeps and your delays and your call laters and that kind of stuff, but it's not a structured system like that. Yep.
So I think I'm a little confused about the syntax for async and await for loops and context managers.
Yep.
You prefix those with async, but I would have thought that you're awaiting the value of the generator as opposed to.
Well, this is the important point is async and await they're native coroutines. They are no longer generators. You can
Right.
wrap generators to become.
Right, but when you're, sorry, so I was saying specifically for the for loop, for example, you
Yep.
prefix the for loop with async as opposed to await.
Yep.
And I would think that you're awaiting each element of that iterator or generator.
You actually are. So it's calling next here, and this is an asynchronous function. So
Okay.
imagine a database cursor,
Yeah.
right? Give me each record individually or something like that.
I just would have assumed that it would prefix the for loop with await as opposed to async, because if you're waiting.
You know, in the PEP, actually, I don't think I have a link to it, they talk about that, why they pick certain keywords for like async there. Oh, it's because what if you want to yield out a for loop as a generator, right? Or other things later on down the line, right? So await is sort of a yield this value out. Async is an indication of what kind of values this object would yield. Does that make sense?
Yeah.
I think that's what I remember from it. But if you go look at the PEP for async await, they actually, there's a whole line of, why did you pick this word? Why did you put this? Why didn't you put it after the for? Why didn't you put it before, like after the def? So, what else? Yeah.
Are there any limitations on what data types you can pass around? So for example, if you're going to use these for different processes,
Mhm. You're only limited by the same thing that multiprocessing or any other ones would be. There actually are a few things. There's like there's a async IO queue that's sort of like a threading queue or multiprocessing queue or other things. If you're doing pure coroutines and you're not using a threaded system or multiprocess system or anything underneath it, then there's nothing that keeps you from sharing raw Python objects that you can mutate at will, other than hopefully some point down the line, debugging and common sense. But like there's no real limitation there because they're all running in the exact same thread. So, but there are a few mechanisms for that, the queue and other pieces. And I don't know what serialization issues they have. Obviously, if you're going to a multi-processing oriented one, then you're probably going to serialize something inside that bus. But I mean, I don't know whether it uses pickle or other things if you pass in raw Python objects into that. But I don't know. Any other questions? Yeah.
If anybody else is interested in G-Event after reading that blog post, there was actually a really good talk at Icon this year. There was like a deep dive into G-Event, like that sounded like a little.
Did it talk about async IO at all?
No, it was just G-Event.
Okay.
But it was pretty instructive.
Yeah, because I'd love to see G-Event pop in there too and use it as the underlying, like, okay, now we're using async IO, there's work in UV loop, now G-Event gets the benefits of UV.
Yeah, this
Right,
is for a
live
user of G-Event, not a developer.
Okay.
You said you found that where?
Icon, it's like just search for deep dive G-Event Icon.
Cool. Well, I will put this up on, under that again, there were some code examples and other things I didn't get to. If it's useful, I'll put it up on GitHub and share that link, but thanks for letting me talk at you for a little bit.
That's really good, thank you. Hey, everybody, please give another hand for Josh. He's really good. All right.
Now somebody sponsor the next meeting with Kevin.
Andrew.
If people are fans of science fiction, ArmadilloCon is this weekend, and so it's our local science fiction convention. It's more of a literary convention, so you don't expect people wearing, Comic-Con kind of things. It's really more.
Can we if we want to?
Yes, they do have.
Will you be? I'm just curious.
I will not.
Okay.
But it is a really fun convention in terms of if you ever had pretensions of writing a science fiction novel or see how it's done, the writers are there talking about the craft of writing. So it's a very different convention than most. But it's this weekend, and it's $55 for a 3-day pass, but you can do just a Saturday pass, which is the big day of the 3
Armadillo Con.
Armadillo Con.
Cool, awesome. Anybody else have any announcements? All right, I think there's still some beer back there. I think there might be some parts for tacos left. So, by all means, please, like, you know, have some beer, have some pizza, or pizza? Tacos. Tacos, not pizza. Come on. All right. Well, I think that is. Anybody have a lightning talk? No. All right. I think that's it for this program. Thank you very much. Thank you, each and every one of you. Please give a hand to yourselves for coming out. Appreciate it.
Thank you for hosting.